Okay, so here we're going to look and start studying chapter 11. And in chapter 11, we're going to look at the hypothesis test and CI on two samples of numerical data. Today, we're going to study what we call independent numerical data. And what this means is that one sample doesn't match up one for one with the other sample. So I'm going to give you an example. I'm going to give you a little information. I'll give you a little example. Not that we're going to like work through the example, but just give you a little example so you can understand. So what we're doing with independent numerical data, we're going to study the same variable from two populations. And what we're looking at is the difference of the two means. So this is still inferential statistics, meaning we're going to study a sample and see what's going on with the population, right? So what we're trying to study is the difference of the two population means, and we're going to use the two samples to do that. So just like a simple little idea example here, maybe we have some RIT students and we have some U of R students, okay, and we're going to survey. And we're going to ask the number of miles you live from school. Or you could say, how far are you from home, right? How many miles are you from home? And what we're looking at is for RIT, we're going to have an X bar and we're going to have an S. Remember, X bar is sample mean, S is sample standard deviation, and we will have an N. So this is my group one. So I'm going to put a little one for my notation so I can keep them separated. For you, I'm going to ask the same question, how many miles you live from school. And we're also going to get an X bar here, an S over here, and an N over here. And I'm going to use a little two for notation for group two, so I know they're different, right? These are different values. And what I want you to know is that the sample sizes can be different. They don't have to be, but they can be. And that's what I meant before when I said they don't line up one for one. So it's not like the individual from here goes with the individual from here, right? Separate individuals for each one. There's no link from one to the other. So that's why they're independent samples. So we're going to get these values for each sample. And what we're going to do today is study the difference in the mean, so the average. So what the mean is, it's the average miles that the group of RIT students that I studied live from school, and the same for the U of R. So yes, we might see that there's a difference in the sample. What we want to know is the difference, is it a statistical difference? Meaning, is it a big enough difference to actually say that there's a difference? Okay, so we're going to study this for CIs and hypothesis test. I feel like this already looks so similar to the ideas of what we did with proportions, right? Where we looked at the difference between the two proportions. Okay. So let's talk about the CIs first, and then we will move on to the hypothesis test. So for my CI, my formula, of course, the same thing as always, point estimate plus or minus margin of error. Okay. Remember, the point estimate is our best estimate. Let me write this. I feel like my markers aren't happy today. This is my, oh, there we go, maybe. Best estimate. And it's not just the best estimate for one mean, but for the difference in means. So it's the best estimate for the difference in my population means. Okay. Excuse me. So when we're looking at point estimate, we're going to look at the subtraction of the two sample means. Now I'm going to use a little notation of 1 and 2 to show group 1 and group 2. And remember, order of subtraction matters. We're going to get to that when we interpret the CI a little bit more. And plus or minus my margin of error. So this is going to look similar to last class where it's my T at alpha divided by 2. Remember, alpha divided by 2 is my location times my standard error here. Okay. So when we're looking at my T, remember this T value depends on a couple things. So this depends on my degrees of freedom, right? And it also depends on my confidence level. Remember from last class, it depends on degrees of freedom because my T curve changes based on my degrees of freedom. Now, you'll notice I just put a line here. I didn't fill it in. Normally, I would fill it in and say, oh, well, degrees of freedom is n minus 1, like I did last class, right? But degrees of freedom is no longer n minus 1. Degrees of freedom is a big calculation. And you can find this calculation on page 3. I'm going to write that down on the typed notes. So the equation for this is on page 3 of typed notes. We're not going to do this by hand. It will be given from Minitab. If you want to look at the large equation, you may do so, but we're never going to do this by hand. And so I'm not even going to show it. If you would like to, you can look it up on page 3 of the typed notes for day 13. So it's also based on the confidence level, right? So if it's 90, so remember we're looking at the curve, we're looking at the middle 90, middle 95, middle 99, that kind of thing, okay? All right. So remember, we never are doing this by hand. Anyways, I just like to go over what's happening. Let's talk about the interpretation. So last class when we had just a single sample of numerical data, I didn't go over the interpretation, and that's because it's like the same interpretation. And this is as well, but I like to give this one because I have to throw in the word difference. And I want you to see specifically where I place the word difference, okay? So here for my interpretation, here we go, of my CI, we're going to say we're going to start it out all the same. So whatever my confidence level is, percent confident. Remember, you can write it any way you want. I just like to give you a template. That the population difference in mean, and then you're going to fill in with your variable, is between your lower and upper bound. So, let me put this in here. Level of confidence. I don't think that's a surprise. Here, you're going to put in what your variable is. So what you're studying. So what is the mean on? And here, you're going to put your lower bound of your CI and your upper bound, which of course you get from Minitab now. Okay. So what I want you to notice is this word difference. I definitely look for this. So if you noticed on last exam, if you missed the word difference, then there was definitely points taken off because that's a big deal, right? Because that's telling you what you're studying, okay? So remember for my CIs, I'm looking for very specific pieces. The pieces I'm looking for here are my confidence level, population difference, and means, okay? I'm looking for the specific wording. I don't want difference moved around here in this statement. I want to see it as population difference in means. And you're going to see next class why that wording makes sense, okay, in this order. And then your mean is of what variable, whatever you're studying between those. So you can switch it around all you want, but this population difference in means cannot be switched around. This needs to stay right the way it is, okay? And if you remember from categorical data, when we looked at the difference between two populations, we had a follow-up, right? So I'm going to, let me just do it a different color. I'm going to say plus a follow-up statement. We don't want to forget the follow-up because the follow-up is what's actually addressing the difference, right? So this is interpreting our results, but now we want to say, okay, well, what is it telling us, right? What are the results telling us? And that's what that follow-up statement's all about. So I'm not going to go into too much detail because we've already gone over this with proportions, and I think most of us got this. From grading the exams, I feel like everyone's pretty much on the same page with all of this. So for my follow-up, let me just write this here. CI follow-up statement, okay? We have three options, right? And so the three options would be if we had an all positive CI, and this means that the entire CI is all positive or above 0. Okay, so we have a difference. I say I'm not going to write it out, and here I am. We have a difference. And what this means, because the order of subtraction matters, is that group 1 is larger than the group 2 mean. That's what this means. So I have three different things here. Okay, let's do that. So I have my CI is all positive, it's above 0. We have a difference. Group 1 is greater than group 2 because when I'm looking at these CIs, what we're looking at is the group 1 minus group 2. Okay. That order of subtraction matters. And here it is. We can have an all negative CI, right? So this means the CI is all negative. Means it's below 0. And the only reason why I care if it's below 0 is because that's what's telling me which group is larger. So we are showing a difference. And this means that group 1 mean is less than the group 2 mean. Okay. And then the third option we have here is if the CI goes from negative to positive, meaning that the CI includes 0. that means we are not showing a difference. Because if 0 is in my CI, that means I do have a chance that when I subtract the two means that they are the same. Okay, so we are not showing a difference statistically. Okay, and that's because 0 is in the CI. So this page right here doesn't just give you your follow-up statement. I mean, you have to write it up yourself, but it gives you the why, right? So, and it gives you all that information. So if you have a CI that comes out all positive, you would say, we are showing a difference, and that is because my CI is all positive, it's above 0. And what I'm showing is that group 1 mean is greater than group 2 mean. So I'm giving you all of this information, and this is exactly like something I would ask, or maybe I might just say, what is your follow-up to this, right? How would you interpret what's happening here? What does this mean for the two groups? Okay. All right. So that's my CI. So let's take a look at the hypothesis test, and then we're going to do what we did last class. We're going to look at two, well, it's one example, but it has two questions, one for the CI and one for the hypothesis test, just on the same data. So I want to go ahead and look at that here in a few minutes. So the hypothesis test this hypothesis test is called our two sample t-test. Okay. It's the same thing as what we were doing in the CIs. We're testing to see if there's a difference between means. So it's the same thing here. Okay, so let's quickly look at the 5-step process. You know, I had someone yesterday ask me still if we still do the 5-step process. Yes, always, all throughout the entire course. We're never going to stray from that. So I might shorten some steps as we move along. But when I say a hypothesis test, it's always a complete hypothesis test. Okay. And that's why I show you this right here. This is what I'm expecting to see. So in the population step, remember we're describing the population, but we don't have just one population here, right? I have two samples. Two samples indicates I have two populations. So we want to identify or describe or list, I'll just say list because that's fine, list the two populations. It's fine with me when someone says, oh, we have two populations, it's RIT students and U of R students. Great, perfect. Gets the point across and it's super simple, I like it. So we only have one variable, so we want to identify the one variable, okay? We have the variable. So here it's only one variable, the same for both. Whoops, for both. I started writing populations. Populations here. Okay, so we're going to study the same variable on both. We do want to define the unknowns. So my unknowns here, and I know this is sometimes a pain, my unknowns, we have two of them, right? So we have population mean 1 and we have population mean 2, and we want to define them. Remember back in categorical data, we have these means and we're going to take this mean and we're going to define it for group 1 or population 1. And then the mean 2 is going to be defined the same way, but for population 2. So the wording is the same and you can type it up once and then copy and paste it and then just change for what group you're studying, okay? So let's say we're going to define these. I don't want to just see mu1, mu2. I want you to say mu1 is the population mean, and then the variable and the objects together. And of course, our goal. Now, our goal is to show some kind of difference, okay? So, show a difference between mu1 and mu2. And you know, don't write this out in symbols. This is all in words, right? And I want it specific for the variable and the population. But the difference could be where they're not equal. The difference could be where one's less than the other. The difference could be where one is greater than the other. So I'm just going to leave it with the symbols like that. But I want this out in words. And you're going to see when we look at an example. So it's not always just not equal. It could be that one's less than or one's greater than, okay? So we'll be a little specific with the goal there. And then we're going to take a look at our method. And you know our method is going to relate directly to this right here, to our goal. So for our method, we do have a couple ways we can have our null and alternative because of this right here, right? So remember, our null is always the same here. So our null is always that mu1 equals mu2. But we can write it the same way that we did with proportions, if we remember. So I'm going to say or. We can write it where the null is mu1 minus mu2 is equal to 0. So you can write it, this means that they're the same either way. It means that the two means are the same. So you can write it either way you want. I'm going to write over here the way you would write the alternative to go with either one of these. Some people mix them up. It doesn't matter to me as long as you understand that the null is that the two means are the same and the HA is that something's different, right? It's the same idea as we had in categorical. So for my alternative over here, so I would say, okay, well, my mean 1 does not equal my mean 2. Or I could say something like my mean 1 is less than my mean 2, or mean 1 is greater than, right? Go with what the problem is trying to show. Or if I wanted to write it like this, where it has, well, it's related to 0, then I would say, well, mean 1 minus mean 2 is not equal to 0. That means there's a difference. Or less than 0 or greater than 0. Okay, so we can write them in these different ways. Okay, like you guys to choose which way works for you. And of course, we're always going to report alpha here. Remember, alpha is always the same idea, 5% most of the time, unless it's given to us, or 1% if it's medical life or death. And again, we want to report what curve we're on. We're on the T curve with degrees of freedom. And that's all you have to fill in there. Okay. So that method step goes real quick. You know, the sample step's kind of like our quick and easy step. So for my sample step, I'm going to include the mini tab here. And now I want you to start thinking about last class. Think about last class. We had our requirements, right? We have 2 requirements for our numerical data. We are required to check for normality, right? So that we have a symmetric bell-shaped curve. And we're required to check for outliers because we don't want those outliers. Those can skew our data and it can kind of mess things up, make things look different than what they really are. So we need to check that, but for both samples, okay? So for my requirements, we're going to check these. So the first one is I'm going to check for normal. Okay. And I need to check for both. So let me write this here. So individually, you're going to check for normality for both. So remember here, I can use n is greater than or equal to 30, or I'm going to look at NPP with the normality test. And remember, for that normality test, what you're looking for is you're looking for a p-value that's greater than 0.05 in order to say that it's normal, okay? So those are the two ways to check. You're going to do it twice, right? And we're going to check for outliers. Remember, checking for outliers can only take place if I have raw data, right? I can't do this without my raw data. The only other way you could do it is if you have a 5-number summary, but it's so rare for you just to have a 5-number summary and not raw data. But I mean, I guess it could happen. So for outliers, you're going to build a box plot and check. So I'm going to say only if you have raw data. I will still get people asking me, or 5-number summary. Okay. Once we check these requirements, I just want you to write a little statement. And I actually typically write it after each one. So I normally say, oh, n is greater than or equal to 30. Okay, I've met my requirements. Or I check it like n1 is greater than 30 and n2 is greater than 30. Okay, I've checked my normality requirement. Good, both normal, something simple. And then I would show both box plots and say, okay, neither have outliers and good. But you don't have to do it that way. So you could do all this work and then down here write like one quick statement about both, that you've met your requirements because you've met normality for both and outliers for both. So you have 4 things to do here, right? Because you're checking normality for 2, checking the box plot for 2. Okay. So I'm just going to say, write a little summary. And so what I mean is that you can write the summary after each one, like I would typically do, or you can write one summary. Okay. Just saying what you found. My results step. We're going to cut this down just a little bit. So I'm just going to go right into interpreting the test statistic. And I'm just going to say the difference in sample means, or you can say X bars, is whatever my test statistic is. Remember, we use the absolute value. That many standard errors. Then it's above or below, because that means if I'm positive or negative for my test statistic. So above means my test statistic is positive, and below means it's negative, and it's not related to any specific number other than 0, right? Because 0 is my mu naught, my null value. And then I just want to add with degrees of freedom equal to whatever they are. From Minitab, I'm going to put. Okay. So we're going to just write the statement instead of reporting them and writing the statement. Of course, if you want to report them and do the statement, you can, but this is what I'll be looking for. And then I just want you to report that p-value. Okay. We'll just report that. And then we're going to move right on to our conclusion. I'm going to squeeze it in here. Okay, so then my conclusion, same as always, is the p-value less than or equal to my alpha. Yes, I can reject, or no, I cannot reject. And then I'm going to have my conclusion statement. the same one as we always write our conclusion statement. Any questions on the process that we're going to be working with? The main difference here, I want to keep using the word difference, but the main thing you're going to see that's changed from last class is this right here, difference. Normally you would say the sample mean is this many standard errors below, right? So difference, this will always be 0 here. It's never going to change. When we're looking at my null, my value of mu naught is 0. Maybe I'll make a note of that so we have that. So I'm just going to write this. This is going to be the mu naught value. That's my hypothesized difference, right? My null. Okay. All right, let's take a look at an example, guys. So let's go ahead and look at, what page is it? Page, I don't think this is right. I have page 8, but example 1, I have page 8 written down. I'm not sure if that's correct or not. So I'm going to share my notes. Feel free to follow along if you would like on your own computer, or if you want to follow along with the screen that I'm going to share. I also have some raw data to download, so feel free to do that too at the same time for Minitab. So let me share this screen here. Remember, we're on day 13. And it is page 8. Look at that. I just thought it was further down, I guess. Okay. Example 1. Remember what I mentioned a few moments ago, that example 1 actually has 2 problems built in. We're going to conduct the hypothesis test, and we're going to create the CI and interpret the CI, all for the same problem in the same data set. Okay. So let's take a look at what's going on with this problem. So we're studying this from this medical center, and we're looking at the cholesterol levels of heart attack patients. And we're also going to look at patients that did not have a heart attack. So what we have are patients' cholesterol levels 2 days after a heart attack, 4 days after, and 14 days after. And then we have what we call control group. Those are just people that did not have a heart attack. And we collected that data as well. So their cholesterol levels. So like I said, I have my Minitab data, and I actually just want to show that to you really quick. So we're going to see question 1 says, let's draw up a hypothesis test. And then 2, let's look at a 95% confidence interval. Okay. And then the question under 2 says, does the data provide evidence that the heart attack patients have an elevated cholesterol level? Okay, so let's keep that in mind. We want to know if those heart attack patients are showing elevated cholesterol levels. So let's see, right here it says, we're going to study the 2 days after the heart attack and compare them to the data of the controlled group, so the people that have not had a heart attack. So what we're going to look at, the difference in means between someone, these patients that had a heart attack 2 days in their cholesterol level 2 days after that heart attack, and a separate group of people that did not have a heart attack in their cholesterol levels. Okay, so I kind of want to show you this Minitab. I'm hoping I did download it. I tried to do this beforehand. Okay, so I just want to show you this data right here so you could get an idea of what we're looking at. I'm just going to move this up so we can see it. Okay, so we can see here we have 2 days after, 4 days after, and 14 days after. So this person in row 1, this is the same person, 2 days, 4 days, 14. And then in C4, row 1, so column 4, row 1, this 196, right? This one right here, that's a separate person, okay? That's someone that has not had a heart attack. I'd just like to show you that. So we're actually going to study column 1 and column 4. Now, in some classes, some students say, well, can I just delete column 2 and column 3 since we're not going to use it? Go for it. If that makes it easier for you to look at your Minitab, then go ahead and do that. I don't do that. I typically just keep in mind, okay, we're going to look at C1 and C4, and I just stick with that. Okay. All right. So just wanted to show you that data because I think it's nice to kind of see and you get a feel for what we're looking at. So I'm going to go back to our typed notes and I'm going to scroll down to the next page where it's a completed example so we can look at the write-up. So for my population, remember what I want to do is I want to identify my two populations. So my first population is my heart attack patients, and then my second population are the control patients, or you could say the non-heart attack patients, right? And then I want to identify the variables. So what are we studying about those patients? It's their cholesterol levels. Okay. It is numerical. Right now, that's all we're doing is numerical, right? And that's another thing, right? We want to think about how do we know this is numerical? Well, when you read through the problem, it says we're looking at someone's cholesterol levels. That's measured by a number. It's a meaningful number, right, for each individual. So right there it is. That's numerical. All right. Then I want to define. So mu1 and mu2. And instead of calling them mu1 and mu2, I actually have it where mu HA is the mu for my heart attack patients and mu control, or you could do NHA for non-heart attack patients, anything like that. It just keeps them separated a little bit clearer than 1 and 2. So mu HA is the population mean blood cholesterol level for heart attack patients, and mu control is the population mean cholesterol level for non-heart attack patients. So my goal, okay, now I need to see what is my goal. Remember what that question was? I'm just going to scroll back up. The question right here, does the data provide evidence that the heart attack patients have an elevated? Well, elevated would mean higher, right? A larger number. So we're wondering, is the average cholesterol level higher for the heart attack patients than it is for the non-heart attack patients? So this relates directly to my goal. So right here, the population mean cholesterol level for heart attack patients is greater than that of patients in the control group or for the non-heart attack patients. When I have this, I'm already visualizing what my method step is going to look like, my write-up. So here you can see I compared it to 0. Remember, there's another way to write it, and you can write it either way. It doesn't matter to me. So here for my null, I have mu1 minus mu2, which I really should have HA and then control, right? That's how I have it defined. I should probably do that. HA and control. I'm going to change it right now because it kind of bugs me. Because you should have it how you have it defined. There we go. Okay. So there. So my HA minus my control equals 0 is my null, right? It means there's no difference, that they're the same statistically. And my HA is that my mu for my, sorry, I said HA before because I was saying heart attack patients, so that I could see it's confusing. My HA for my heart attack patients minus my control is greater than, right? So if it's greater than, that means it's a positive answer in the end. And that means that this group is higher. Okay. My alpha is 0.05 here. It probably should be 0.01. I mean, heart attacks are pretty serious, right? Could be medical, life or death. Remember, if you're choosing and it's a problem like this, you choose 0.01, I would definitely go with that. Like I wouldn't say, oh, it's 5% because that's what I chose. No, I would definitely agree with you. So don't feel nervous about that. Remember, we're going to mention that it's the T curve or T test statistic or T value, anything like that with degrees of freedom. Now we get to our sample step, and this is our mini tab. So let's take a look at our mini tab. Let's work through this. So remember, this is going to look different from last class because after all, we have 2 samples and we're studying a 2 means and not just 1. So we're actually going to start off in the same place where we went to stat menu and basic, oops, if I could do it right, basic statistics. Okay, so we're going to start off in the same place of stats, basic statistics. And we're still going to go in like the second grouping here, but I want you to think about what we have. We're studying a T curve and we have 2 samples. So we're going to use this 2 sample T today. So I'm going to click on this. Now, remember what I always have to do is I have to be able to tell Minitab if I have raw data or summarized data. Raw data is what we have here, right? I have 4 columns with a whole bunch of numbers. That's raw data. Summarized data would mean that I give you a sample mean and I give you the sample standard deviation. Don't have that. I have raw data here. So I have both samples are in one column. And now, so this is going to throw in a little mix. Here's my summarized data. And then I have each sample is in its own column. So remember how we talked about stacked and unstacked? Here it is. So here we have unstacked data. So I have 4 columns with their own numbers. Stacked would mean I would have one column with a whole bunch of numbers, and then the other column would say 2-day, 4-day, 14-day, control, you know, and go and like that. So it would line up. So this is unstacked. Stacked would be all of the data in one column. Okay. So this means I have each sample in its own column, right? Because I already said we're going to study column 1 and column 4. Okay. So sample 1. Now this is where you need to note which one's going to be your sample 1 and which one's going to be your sample 2. You need to know it for you because the order of subtraction matters. So sample 1, I'm just going to go ahead with the 2-day. And sample 2 is my control group. Bring those in. Let's just check out options and see what happens here. So we could see what happens and we could see what it looks like. Look at right here, difference, sample 1 minus sample 2, because that order of subtraction matters. Here's my confidence level. So when I get to my CI, I can change that all I want. Remember, for a test, it doesn't mean anything. That's the default at 95. My hypothesized difference, this is my null. Remember, it's always 0. This is not going to change from 0. It defaults to 0. We're not going to change it. It is 0. So we're going to leave that the same. And now here, my alternative hypothesis. I need to change this to match my HA. Remember, the HA we said was a greater than. So we're going to stick with the greater than there. Okay. And see this little box says assume equal variances. We are not going to check that. We are not going to assume equal variances. What that means is we're assuming equal spread. We are not assuming that. These are independent samples. Okay, so we are not going to check that. So leave that one as it is. Okay. I'm going to click OK twice. And we're going to get a whole bunch of output here. Look at what's going on here in the top. It actually describes mu1 is the 2-day, mu2 is the control. So this is when it's nice when you have labels for your columns. So it actually has them here. And then you can see that order of subtraction and make sure you have it the correct way all the way along, okay, for your write-up and your Minitab. So look at, we get some n values. We can see they're different. We get a mean, standard deviation, okay? Remember, we're only going to get a lower bound or an upper bound here because we're not looking for a CI. We chose the greater than, right? So remember, it's only going to give me one value if I do greater than or less than, but it's okay. We're not studying the CI right now. Right here, this is my interest right here. Although I bring everything in, what we really need to see is this. I like to bring it all in because it has all the information, but this is what we're looking at. So I'm going to bring this over and take a look at the Minitab in the I'm like struggling in the typed notes. Okay, so I have someone in the message saying they can't get the output because there are more control values than I know they're different. So did you use the right test? Did you do the 2 sample t-test and choose that each sample is in its own? So try that again. Make sure you're going to 2 sample t-test and you're choosing the option, right? So there's summarized, there's everything's in one column, or the 2 samples are in their individual columns, not in one column. So try that out. You've got it. Awesome. Great. Okay, So here's all my output, a whole bunch of information here. Now I need to check my requirements, okay? So to check the requirements, I need to build box plots to check for outliers, and I need to check for normality, okay? So if I'm looking here, my N right here, 28 for day 2, that's not greater than 30. I need to draw an NPP for that. I need to do the normality test. For my control group, it is 30. So I technically could just say that one's normal and move forward with the central limit theorem, just saying N's greater than or equal to 30. I'm good to go on that one. And then I need to draw my box plots to see if there's any outliers. So let's just make our way back to Minitab just so we could check that out. So I'm going to do everything separately. So I'm going to go into graph for my box plot. Halfway down, you'll find box plot. I'm just going to take a look at a simple box plot. So I'm just going to look at them individually, and I'm going to take a look at the 2-day. Remember, for the box plot, you can add different things. You can change it around. You don't have to. I'm just going to click OK because I just want to be fast and get through this part of the testing process. Take a look at that. No asterisks on the top or on the bottom. I'm good to go. There's no outliers. So that was for the 2-day. So let's take a look at the same thing, but now for the control groups, I'm just going to remove the 2-day and add the control group and click OK. And now I'm just going to take a look at this one. Again, no asterisks on the top or on the bottom. I'm good to go with that. So there's no outliers in either set of data. So that's great. Now I want to take a look at my NPP specifically for, I believe it was the 2-day. So let's go look here. Yep, the 2-day. So when I'm looking at this, remember I'm going to go to graph and it's a probability plot. This is really good practice. So it doesn't matter if you do it on both. It's really good practice. I'm just going to do single because I'm just going to do one at a time. So I'm going to bring in that 2-day and then just click OK. Does look fairly linear, but again, I want to take it that step further and run that normality test. Remember the normality test. I'm looking for my p-value to be greater than 5%. It certainly is. It's almost 26%, right? So it's 0.259. So with a p-value greater than 5%, we can assume normality, right? You just do a little brief write-up on that. If we wanted to do it on the other one, we could. I want you to know sometimes I will tell you specifically because sometimes it doesn't always match up just right. Meaning that your N could be greater than 30 once in a while and your NPP might not look right. That's why we always just go with N greater than 30 first. All right, so I'm going to go, oh, I'm sorry, not box plot, probability plot, wrong one. Here it is. I'm just going to check it out for the other one. For my control, let's click OK. Here it is, and it's 0.09. That is still greater than 0.05 for my p-value, so we are good to go there as well. My p-value 0.09 is greater than 0.05, so we can assume normal. Okay. So let's take a look. So here for my requirements, you're going to see I'm going to include all my graphs, and look at this. I made my box plots the same. You can play with that. You can do that too on the probability plots. Sometimes it's just easier to do them individually and then move on, and you're not second guessing what you're doing. If you want to play around with things and put them both on one, feel free to do that, okay? At this point, I'm not going to require you to put everything together right now. So everything separate works fine. I just have like little write-ups, right? About my normality, about not having any outliers. Look at this for my normality test here. So my null is that I assume normal. I cannot assume normal. And then I do one write-up right here. So the heart attack patient's p-value is 0.259, control is 0.099. Therefore, normality has been met for both. You can write it like that, very simply stated. You don't have to separate it out, even though I have to. You can address them both at the same time. Okay. So that seems like a little longer, but I think it will go fast once you're doing it on your own. So results. Remember the results are from my output here. Look at my test statistic is 6.15. My degrees of freedom is 37, and my p-value is very small. So I'm just going to say that the difference in my X bars is 6.15 standard errors above 0 because it's a positive number, the 6.15. With degrees of freedom equal to 37, my p-value I'm going to report as small. Remember, very small, I'm sorry. And remember, this here is optional. I meant to make this Alex. There we go. Okay, optional. Then my conclusion, is my p-value less than alpha? Yes, it is, right? Because it's very small. So we can reject the null. At the 5% level of significance, the sample does provide evidence to say that the population mean cholesterol levels for heart attack patients is greater than that of the control group. Okay. Any questions on the hypothesis test? All right, let's take a look at the CI real quick. CI doesn't take nearly as long. So I'm going to go back to my mini tab. We're going to go back to the same places where I found my test. So that's stat, basic statistics, to sample T. So when I go into the to sample T, I already have everything in here, right? I have each sample in its own column, the 2-day, the control, because I just worked on this. I just want to take a look at my options because I want to get the CI. So that means I'm looking for a 95% confidence level, and my alternative has to be a not equal to get a CI. I don't need to change hypothesized difference. It's still 0. And again, I still do not want to check off the box for the equal variances. I'm going to click OK twice. And right down here, we get our CI. So right here, my CI is 40.75 to 80.84. Okay. So when I'm looking at this, we want to make sure we interpret this properly, right? So we want to make sure that we say we're 95% confident that the population difference in mean cholesterol levels between the heart attack patients and the control group is between 40.75 and 80.84. So you want to add the variable and the context, right? So what we're studying and who we're studying, we want to add it in there. And that difference is the big key word, okay? Then we want to address if there's a difference. Well, look at my CI. It's all positive, right? All the numbers are positive. So yes, there's a difference. So what kind of difference am I showing? I'm showing there's a difference because everything in my CI is above 0. And that means my first group is greater. Well, the first group was the 2-day, right? That was in my group 1. You could see it right here. Mu1 is the 2-day. So that means that 2-day is greater than the control. So it is showing what we were thinking or what we were looking at, that heart attack patients do have a higher cholesterol level. Okay, and you can see the full write-up here. Okay, you can see everything, and we talk about the order of subtraction. All right.